Hello, chemistry students. This is a question from page 525, number 3A. We're going to solve this now and point out a subtle but important difference from this and when you're calculating Ka in other situations. Okay, so the question asks to calculate the acid ionization constant Ka, and it says you have the following information. So you have 0.02 molar concentration of ascorbic acid, and it has a certain pH of 2.4. Now, what it's not saying here, what it's implying is that this is at equilibrium. So at equilibrium it has a pH of 2.4 and a concentration of 0.2. So the acid has a concentration of 0.2. Okay, so let's write out an ice table. Now, it isn't going to be your typical ice table. We have to interpret what's being given to us in the question. So C6, H7O2, okay, in the presence of water. This is aqueous, this is liquid. Okay, so regular ice table it appears to be, right? We can ignore water since it is a liquid. And we don't know much about the initial situation, the initial concentrations. We really don't know what the initial concentration of this acid was. We can hypothesize correctly, I think, that the concentration of hydronium and respective acid ion is 0, right? And that these will, according to this monoprotic acid balanced equation, balanced association reaction, we see that this will change by a value of plus x. This might change by a value of something minus x, or minus x here. Again, we don't know what that initial value is, nor is it actually important, because here we're given what the concentration is at equilibrium at a 0.2 molar concentration. We add I and C, at least for our products here, and we get XX. Right? So our Ka expression, just to be complete, I'll write it out. Right, ignoring water. Okay. Now we have expressions for these, at least for our products at equilibrium. We have a value for our acid at equilibrium, so we should just plug those in. So we get x over 0.2, and we need to figure out what our Ka is. Now we don't know what our Ka is because we don't know, of course we're being asked for that, but we don't know what it is yet because we have to figure out what this value for x is. But the question does tell us that we have a pH, right, a pH of 2.4. That means we can figure out what the concentration of hydronium is given this pH value. So a little side calculation here, we can figure out what the concentration of hydronium is because we're given pH. So 10 to the negative 2.4 is 3.98 times 10 to the negative 3 moles per liter. So we know the value of hydronium, therefore we can say, let's erase that, the concentration of hydronium, which is X, is equal to 3.98 times 10 to the negative 3 moles per liter. Okay, so we know the value for X. Let's plug that into our Ka expression and do a bit of calculator work, and we're done. So we get 3.98 times 10 to the negative 3. I'm just going to square that since x times x is x squared. That divided by 0.2, the concentration of acid at equilibrium, and we get the answer at 7.9 times 10 to the negative 5, which reflects the answer at the back of the book. Hope this helped.